We just got done doing common ion effect problems. The next step after common ion effect problems are what are called buffer solutions. And buffer solutions are the twin sister of common ion effect problems. There is actually no difference between a buffer solution and a common ion effect. What does get difference is the twin sister turns into a very ugly stepsister in the next process. So we got to have a strong foundation of what buffer solutions are, because they are going to lead us into the next step. But what a buffer solution is, it's just a solution that actually doesn't change its pH when you add an acid to it or when you add a base to it. So it's literally a solution. If I put an acid in there, its pH doesn't change. But if I put a base into the solution, its pH also doesn't change by a whole lot. To say it doesn't change is not true. It does change, but not as much as you would think. Okay? So some things that you may have heard of that are buffered, and maybe you haven't. Buffered aspirin is an aspirin that was developed because our stomachs are acidic, and aspirin is actually something that's acidic, so people will get upset stomachs. So they created buffered aspirin. Our blood is actually buffered. Our blood, it has an acid and a salt in it, so our bodies won't get too acidic or too basic. So it's literally impossible to change your pH of your body to a higher or lower pH. And if you go to the web, you can search up people that are actually trying to do that, and it's literally physically impossible to do. So what is a buffer solution? A buffer solution is essentially a solution that consists of a weak acid and its salt at the same time, which is literally common ion effect, okay? So this right here, acetic acid, that's my weak acid, and this is the salt of that weak acid, where the sodium ion doesn't matter. So if you were to write out the equation for this, and I highly encourage you to do that, we always start our equations for buffer solutions with the acid, okay? And that is, I very rarely say always, but that's an always in this case. Okay, so you'll never start with the salt. So if I start with acetic acid and I add it to water, what is going to happen, since this is the weak acid and we know that, we're going to get H3O plus C2H3O2 minus, okay? And the sodium doesn't matter, so the sodium is not part of that ion, but now I have the acid and its salt that actually matters. So this is the acid that matters, and that's the salt that matters. And essentially you can see that this is a common ion right there. So that's all buffer solution is a weak acid and salt. So you can take any weak acid. So I could take HF, okay? And what would be a salt of HF? And pretty much throw any group 1 element in front of it. So KF would be its salt. Again, the K isn't going to matter in this case. So I have the weak acid and I have its salt. And again, if I write the equation for that, this is going to be HF plus H2O is in equilibrium with H3O plus F minus. Okay? So, it's any weak acid and its salt, okay? Or it's any weak base and its salt, okay? And again, all that matters is the weak base and the salt of the weak base, but again, chloride doesn't really matter, okay, because chloride is a conjugate of a strong acid and it's not going to do anything. So when you're writing these equations, again, always start with the base. So I start with the NH3, I add water to it, okay? Now water becomes the donor, so this becomes NH4 plus OH minus. And right here, you see that that is NH4 plus, okay? So again, in this particular case, you have the base and its salt, which happens to be a weak acid. So, again, if we throw numbers in here, this is just going to be a common ion effect solution. So, right now, all we're worried about is calculating the pH of the buffered solution. Okay, we're not going to worry about adding acids or bases to it. That's the ugly sister part that we'll do tomorrow. So, I have right here a buffered solution that is 0.7 molar in acetic acid and 0.4 molar in sodium acetate. Okay, so what I want to do first is write the equation, and again, the equation always starts with the acid. So sodium acetic acid is HC2H3O2. We're going to add water to that. That's going to give me H3O plus C2H3O minus. Okay? And now we're just going to make our ice chart out of this. And what we have is a 0.7 molar of that. Water doesn't matter. This is 0 to start with, and this is 0.4 molar because that is the salt that's coming from the sodium acetate. You know this is the salt because it has the sodium with it. And now, hopefully you just recognize that this is a common ion effect problem. That's all this is. So we continue with minus x, x, and x. 0.7 minus x, x, 0.4 plus x, and we solve. And we know that the Ka is going to be x times 0.4 plus x all over 0.7 minus x. And I can put my Ka in there, which is 1.8 times 10 to the minus fifth. And we can solve this bad boy. And the x's don't matter. And you can do the math to solve. I'm just going to jump ahead here and say that we know what the x is. It's going to be 3.15 times 10 to the minus fifth. I highly encourage you to do the math. Make sure you're getting that. And x is the H3O plus concentration. So the pH of this solution comes out to be 4.50. Okay, so common ion effect problem. Not very challenging at this particular point because you just did a number of these. But what we're going to look at is we're going to change this a little bit. So ultimately, the end result that we want of this is always to calculate what the pH of the solution is going to be. Okay, and this is going to be something different. Since pH is always the log of the H3O plus concentration, I know we haven't written this for a while, but this Ka is the H3O plus concentration times the ion concentration times the original acid. We haven't written that out. We've been writing x's and x's and whatever that is in terms of x. We've been writing those as x's. But you got to remember that deep down, that's still our equation. And what we're going to do is we're going to solve this for H3O. Okay? So if we're going to take this equation and solve it for H3O, that means I would have to multiply both sides by the CH3COOH concentration. That would cancel that, and I got to do that over here. And I'm going to rewrite what I have. So what I have right now down here is I'd have Ka times the acid concentration equals H3O plus times this concentration. And then remember what I'm solving for. I'm solving for H3O plus. So what I'm going to do is divide by that concentration, which cancels that. Divide by this over here. Okay. So rewriting and flipping, what I have is the H3O plus concentration is equal to, I'm going to pull the Ka out, the Ka times the concentration of CH3COOH all over CH3COO minus. Okay? So now, you're going to say, well, why do that? Well, why do that is because right here is the H3O plus concentration, and pH is just minus the log of the H3O plus concentration. So what we're going to do is we're going to take minus the log of both sides of this. Okay, so imagine that being right there. I just couldn't fit it there. And if you do that, this side of the equation minus the log of the H3O plus concentration is pH. Now, you're going to have to believe me on the math here, okay? So what I would do if I have minus the log of this is I would have minus the log of the Ka minus the log of the CH3COOH concentration all over CH3COO minus. Okay? Now, this term right here is actually called pKa. And I'll explain that in a moment. Okay? So the pH is going to equal the pKa, and then this is the math that your math teachers have to deal with, and you can learn and do from that. You can look from them. I'm just giving you the final end result of this. If you flip some things around, this becomes, oops, I used black. This becomes plus the log of the CH3COO minus concentration over the CH3COOH concentration. Okay? And what you need to recognize is this is really the base, and this is really the acid. So, what happens in this, just to rewrite this one last time, is this becomes pH equals the pKa plus the log of the concentration of the base over the concentration of the acid. That is the final equation, and you should go to AP Chem equation sheet and check it off. But this equation is called the Henderson-Hasselbalch equation. Okay, the Henderson-Hasselbalch equation. And basically what it allows you to do is solve a buffer solution without ever making an ice chart. So we can eliminate partially ice charts. Okay, so if you basically take the Henderson-Hasselbalch equation and apply it to the last problem, we can eliminate ice charts as long as we can identify that the solution consists of an acid and its salt, or a base and its salt. So you need those two things. Okay? So if we go back to the problem from yesterday, or previous, the solutions were 0.7 acetic and 0.4 sodium acetate. So recognize acid, recognize salt. And one thing we want to do is we want to calculate the pKa. So the pKa is minus the log of the Ka. So in this case, the pKa would be minus the log of 1.8 times 10 to the minus fifth. So if you do that in your calculator, it's no different than any other calculation we made. This comes out to be 4.74. Okay? So once you make that calculation, now we can just say, okay, the pKa is going to be 4.74 plus the log of the base, that's the base, 0.4 over the acid, 0.7, and calculate. And I encourage you to take your calculators out and calculate that. And when you do, what you will see is this pH comes out to be 4.49, I think is what it actually comes out to be, which is the same essentially as the 4.50 that we got doing it with the chart. Okay, so essentially the Henderson-Hasselbalch equation takes that big huge chart and condenses it down to that equation. So just a few things to note. There is a pKa, okay, which is minus the log of the Ka, but just like that, there's a pKb, which is minus the log of the Kb. However, the way I'm going to teach you how to do this is we will always use pKa, whether or not we have an acid or a base solution. We will use pKa. It won't matter. And then that's another good thing to recognize is pKa plus pKb is 14. But again, I'm going to keep us in this realm. That way we only have to learn one system. Okay? Now, what does this look like? So here's a buffer solution. What is the pH of this buffer? That's 0.12 molar in lactic acid and 0.1 molar in sodium lactate. Okay? You can make an ice chart. Okay, ladies and gentlemen, I'm not telling you you can't do this. You could do an ice chart for this problem. I'm going to tell you you don't need to. What you need to do is do a quick calculation of the pKa, which is going to be minus the log of 1.4 times 10 to the minus fourth. So the pKa in this particular problem is going to be 3.85. Again, I encourage you to do that. But then we can just use the Henderson-Hasselbalch, which is the pH is going to be 3.85 plus the log of the base, and the sodium lactate tells you that that's the base, okay, and 0.12 is the acid. It literally says acid. Okay, so making sure you get the base and the acid in the right spot is kind of crucial, but then this pH comes out to be 3.77. Okay, so what exactly is this pH? Right now it's the pH of the buffer solution, and that's all we're worried about calculating today. is the pH of the buffer solution. And then a little side note, notice I never told you the formula of lactic acid or sodium lactate. Formulas didn't matter. Okay? What does matter is that we know that we're only donating 1 proton. Okay? But the formula of this doesn't matter. We can solve this without a chemical formula. I want to do one more where I talk about a base and its salt, because this is the second half of the worksheet, and for the last 2 problems on the assignment, you're going to want to refer back to this particular section of your notes. So a base and its salt, okay, we still want to use the same Henderson-Hasselbalch equation. I was too lazy to write out Henderson-Hasselbalch, so Henderson-Hasselbalch now becomes the H&H equation. But there are some issues. A base has Kb, not Ka. And this formula has Ka. But we're going to do a quick change where we change Kb into Ka, and then we can still use this equation. And if we do this for bases, then I don't have to give you 2 equations, because there is a Henderson-Hasselbalch equation for POH. We never want POH. Everybody wants pH. So the one thing you have to remember is the Ka is always 1 times 10 to the minus 14th divided by the Kb. Actually, what you should remember is Ka times Kb is 1 times 10 to the minus 14th. But if I just convert a Kb into Ka, I can always use that equation. So here's a quick example. I have a pH of a base. Hopefully you recognize that is a base, and that is the salt of its base. Okay? And I have, I did not give you the Kb. So, sorry, I meant to give you the Kb. The Kb of this is 1.8 times 10 to the minus 5th. And I know, by the way, that that number looks familiar because it's also the Ka of acetic acid. Coincidence. Okay, but I want to use the Henderson-Hasselbalch equation, so I want to use pH is pKa plus the log of the base over the acid. And as you start doing this more and more, that's actually what you'll probably write. So I need to quickly calculate the Ka, which is going to be 1 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5th. That Ka comes out to be 5.55 times 10 to the minus 10th. Okay, again, you should do the math, but that's what it comes out to be. And then if I calculate the pKa of that, the pKa comes out to be 9.26. Okay, so again, you should calculate the pKa just to make sure. So the pH of this is 9.26 plus the log, and now we can still use this equation as the base, which is still 0.25, over the acid, which is 0.4, because this salt, NH4 plus, is the acid. And if you do that, our pH comes out to be 9.05. Okay? So, basically, this Henderson-Hasselbalch saves you the ability, or saves you the time of having to do the ice chart. Just to show you, this problem worked out as an ice chart problem. So you could work this out as a buffer solution slash common ion, because there's my common ion, and you could work it out with our Kb right there, putting our Kb in and calculating POH, and then from POH calculating pH, and you'll see it's the same thing. So the Henderson-Hasselbalch equation essentially saves all of that. So here's where you're at, okay? you have some problems, they are attached in Google Classroom for you to work on. If you have questions, okay, I'll be available during normal class hours. You can join a Zoom meeting. This does not mean you can't contact me at any time, but I'm specifically setting aside class time for you guys, okay? And the Zoom code should be posted in Google Classroom.